Fugacity is one of those things in thermo that chemical engineers have to go through, and we've made a bunch of very dank memes about with our fugacity explanations and how hard it is to explain. And I went through the whole year, and I still have a very difficult time following it, but I'm going to do my best in this video to explain what is fugacity and why it matters. And to begin with, if all you want to know is what is fugacity, it has units of pressure, and it's a way of allowing us to correct or have a corrected vapor pressure term of a component in a mixture. And if we get these dank memes out of the way and now start and we look at what fugacity really is, I think the best way to begin this discussion is to say, let's say we have some kind of vapor-liquid equilibrium consisting of a component A and a component B. And the thing is, there are intermolecular attractions. So if a molecule of A interacts with a molecule of B, they will have some kind of specific interaction between them. And the same can be said of molecules B. So between two molecules of B. And then there is A-B interactions. And so we've got three separate kinds of interactions occurring inside of our mixture. In this case, it's a binary mixture. And in the case that the intermolecular attractions between molecules A and A are equivalent to molecules B and B, then interactions between molecule A and molecule B will be identical. And in these cases, so if interactions between AB are the same as AA and BB, then it's ideal. And in the case that it's ideal, we can turn to Rayoult's law to successfully describe and define the vapor-liquid equilibrium of each component in a flash drum, for instance. But when that is not the case, we need to begin to take into account a few more variables. And in this case, what we get out are things like this. So we'll see a lot of phis. So phi sub k times y sub k times p total is equal to gamma sub k, x sub k, and f naught sub k. And so these are all separate terms, and we're going to look at each one of them. And to begin with, phi k is what we call the vapor fugacity coefficient. Yk, as we know, is just the mole ratio of component K in the vapor phase, and P total is just the total pressure. This gamma sub K is referred to as the liquid activity coefficient. X sub F is the liquid mole ratio. And F naught sub K is what we call the pure component fugacity. In other words, if we're just looking at pure oxygen, for instance, pure oxygen will have a known pure component fugacity, and that's what the value we would plug into this is. And at this point, I would like to make it clear that most of these are generally tabulated values, and you'll be given them. And so if you're given some kind of question on a thermodynamics exam, your teacher would supply you with a vapor fugacity coefficient, a liquid activity coefficient most likely, or you might be asked to solve for it, but these are all values that we can look up. So hopefully you're not too afraid and we're still paying attention, but that is the gist of it. That's why we need to care about fugacity and all these additional components. And now if we begin to consider other systems that we've looked at previously in which we had a nice vapor-liquid equilibrium constant K, we recall we had this term yk was equal to big K times xk. This related the vapor mole ratio of component K to the liquid mole ratio of component K via the equilibrium constant K sub K. And what we can do is we can take this formula here and rearrange it to solve for what K sub K is. So if we perform that, what we'd find, and it's just a basic algebra substitution or moving around, get K sub K is equal to gamma K, the liquid activity coefficient, times F sub K naught, pure component fugacity, quantity divided by Vk, the vapor fugacity coefficient, divided by P total. And with this defined, we can now have a better idea of how a component will mix, or how it will reside in both the liquid and vapor phases at equilibrium when we have multiple species present and it's no longer an ideal vapor or an ideal liquid. Now, it is important to ask, what if everything is ideal? Well, in that case, what we can say is that our vapor fugacity coefficient phi sub k will be equal to 1, as will our liquid activity coefficient gamma sub k, and our pure component fugacity will be equivalent to the vapor, the saturation pressure of that pure component, and this can come from Antoine's equation. And Antoine's equation, as we'll recall, was ln, the natural logarithm, or it can also be log base 10 depending on what your constants a, b, and c are. But in this case, I will leave it like this. We have the natural logarithm of the, and this naught denotes saturation pressure of component K. This is equivalent to A sub K minus quantity B sub K divided by T plus C sub K. And again, A, B, and C are all constants that we know, and T here is just the temperature. And they'll tell you whether or not temperature is in degrees C or degrees Kelvin depending on your constants in the table. And so what I'd like to do at this point is just make a note how pK naught is equivalent to pK saturation. And finally, if everything is ideal, then we can make the claim that our K will boil down to K sub K will be equal to 1 times Fk naught, which we just established was the saturation pressure of component K. And we're going to divide this by our vapor fugacity coefficient, which is now 1 because it's ideal, times P total. And if we continue on and we look back to our vapor-liquid equilibrium, in which we said that Yk, the vapor mole fraction of component K, times P total, was equivalent to xk times pk saturation, we can see quite nicely how K is going to pop out of here. And we will be able to say that Yk is equal to kk xk. And this is the nice Rayold's law, which is for ideal behavior. In other words, ideal liquids and vapors or gases. And so this wraps up an introduction to fugacity and why it matters. And just to recap, we need to use fugacity and take that into account when we no longer have ideal solutions if the intermolecular attractions between components are not equivalent. If like does not equal like unlike, then we need to take into fugacity if we want to have a better model of our system. And this is important if we're designing chemical processes, because we need to know what kind of equilibrium relationships are going to exist in practice if we want to optimize our equipment properly. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.